Hello and welcome to the video lecture accompanying Lecture 30 covering Section 13.6 from Young 14th edition. In this final lecture of the semester, we are going to discuss spherical mass distributions and gravity. All right, so this concludes our discussion of gravity, specifically universal gravity. All right, so let's get into this final topic. So the first thing we want to get out of the way is something called the shell theorem. I'm not going to go into this in any depth because it's beyond the scope of the class, but I want to at least address it as a potential concern. So the shell theorem states that for any spherical mass, the gravitational influence of the mass is only the matter that exists underneath the point of measurement. In other words, if a hole is drilled into the earth, the gravity decreases as the influence of matter above cancels out. Okay? So let's put this in writing. For any spherical mass distribution, the gravitational influence of the mass, that's that mass that's distributed spherically, is only the matter that exists underneath the point of measurement. So all the matter above does not matter. All right. So in other words, e.g., if a hole is drilled into the earth, the gravity decreases as the influence of matter above cancels out. You're not going to be pulled up by the matter above. So the gravitational attraction of the matter above cancels out. Okay, so what this looks like is if we have a spherical distribution of mass and we imagine some point within that distribution, then if we consider the mass within, that is the entirety of the gravitational force that needs to be calculated. And the hand-wavy explanation that can be shown with more complex kind of multivariable calculus is that there's a certain amount of mass that is more or less directly overhead. And that mass is creating a force in this direction, like so. Okay? But there's also mass that is above in the sense of at a higher depth, right? So not as deep as the hole, that is on the other side and also at angles, and that would look something like this. And this mass in general, you can say, well, it's going to create a net force that goes in the opposite direction to the kind of cloud-shaped net force that I argued for the other section. So this would look like, this would create a force in this direction. And thus, all those forces of the matter that's above your head cancels out, because some of it in this case is to the right and some of it's to the left, and there ends up being an exact cancellation. The only assumption being made here, incidentally, is that the mass is distributed uniformly, not with depth, but with radius. Well, that's actually really misleading because the radius is the depth, but with angle. So all we need is that to have no functionality of the density that is a function of theta. So phi cannot be a function of theta if theta is thought to be measured in the circular direction. Okay? So that cannot happen. We can't, because then of course it wouldn't cancel, because perhaps the denser section is the one that's directly overhead. Thus, this section would be a greater gravitational pull than this section, right? But we need those to be equal and thus cancel out. Okay, so hopefully that makes sense. Again, not proven, but stated. But gives you some peace of mind, because at least it sounds believable, right? But of course, we can leave a proof for another day, not in this particular class. Now, I want to start with giving you a couple formulas. These can be derived with calculus. We've done similar approaches, and we're going to do a similar approach in one of the examples. But I decided not to include the derivation, say, in the key formulas. And I simply want to state them and then kind of jump into a couple of examples. So the formulas given here are simply the mass inside of a sphere, so that's encased in a certain region of the sphere, and the force inside a sphere. Okay, so let's label these as such. So this is the mass inside a sphere of uniform density. Okay, so what's going on here? Well, it's simply saying then that the mass encased in a sphere, and that is the sphere with radius r. Now that need not be the total radius. Okay, so r could be, I'll put it over here, r could be less than or equal to big R. And I won't go into depth of labeling those, but simply the idea here is I want you to think of r as the variable. That could be like your depth within a sphere, such as up here. At least we can kind of illustrate it in the picture above. So this could be the variable r, right, some distance from the center. But the fixed value, big R, is the actual physical quantity of the world, right? That's how large it is. You just may not be on the surface. Okay? So that's the idea. And so then the total mass within is simply the volume, 4/3 pi r cubed, times the density. Okay? Because density has units of kilograms per cubic meter. Here, this is the volume in cubic meters. That, of course, gives us our total mass. And if we have uniform density, then our rho ends up being exactly the mass per volume. So then what cancels out is, well, all of the characteristics that are specific to the shape, right? So if I can elaborate on that, let me do so. And this is, so we could say because rho uniform, so this would be true of any uniform density sphere, is just going to be the total mass over the volume. So it's just going to be m over v, where m represents the total mass. Just like big R would be total radius, big M is total mass. Okay? And so then this is going to be m over, well, the volume, of course, is 4/3 pi big R cubed, right? Because this is the fixed volume. This isn't the variable volume. This is the total volume, okay? I'm not putting subscripts of TOT or anything. We just uppercase implies total. Well, when we do make that substitution for rho, we get our big M. Our R cubed is going to be along for the ride because it didn't show up, but the 4/3 pi cancels out in both the denominator here and the numerator here. And so then we're just left with the following ratio. Okay? So essentially what that's telling us then is we have a ratio where the mass enclosed is proportional to the radius cubed. So if you think about it, then if you have an r, this is just, I will erase this in a minute, but if you have an r that is equal to 1/2, so little r that's equal to 1/2 big R, well, then you're going to be enclosing not half of the volume, right? Or I should say not half of the mass. Not even close, right? I mean, if you think about what that would be, well, you'd cube it, and so what would that be? 1/8, all right? 1/8. Okay, so the mass enclosed would be 1/8 the total mass if R was 1/2 of big R, okay? Because it would be 2 to the third power. 2 to the third power is 8, okay? So it would be m/8. And that's interesting, right? We haven't spent a lot of time talking about mass distributions, although we have, done things like the spherical distributions in order to find moments of inertia of spheres that have non-uniform density. But I think this is a good encapsulation of ideas that really shouldn't be looked over, right? These are fundamental ideas about how volume scales with radius, all right? And how mass scales with radius, at least when you have a uniform density. Well, anyway, so getting to the force business part of it. So if you look at force, well, then this would be force inside. And this is the gravitational force inside a sphere of uniform density. Uniform density. Okay? And again, this would be little r less than or equal to big R. And so what's going on in this case? Well, the idea then is that you just get universal gravitation. That's what all this is, just garden variety universal gravitation, G, M, M over R squared, okay? Of course here, M is the mass enclosed, okay? So then when we substitute that in, that changes things. Then we end up with a r cubed up top and r squared in the denominator. That means that we can't have quite a bit of cancellation, and we're left then with a force that is proportional to a variable of little r to the first power. So it's actually linear. So the gravitational force scales up at a linear rate. Isn't that fascinating, right? And this is super important. This actually is the same sort of relationship you would see if, say, like charge inside of an insulator, right? Encased charge. All right. So let's graph that. I think that will kind of drive home the point quite well. So if I have a graph that has the force of gravity on the vertical axis and the radius on the horizontal axis, then we can imagine a point where little r equals r. That's right where we get to the surface. And it turns out that when we graph this, we see clearly that we have our linear relationship up until we get to r. So I'll actually I want to make this clear for me as I draw it. So let's have a little r go up a bit. There, that'll do. All right, so we'd have a linear relationship that increases up to some maximum value, like so. Okay, and so that's for r less than r, big R, okay? And it's growing linearly. But then afterwards, well, then it just becomes universal gravitation. It's just a point mass at that point, because the spherical shell argument can be argued for once you're on the surface and moving away, so you don't have to worry about the distribution anymore. It's immediately treated like a point mass, okay? And so it's going to fall off as a 1 over r squared function. So it looks like this. All right, so then we end up with a linear region here, so a proportional to r, and over here we have a proportionality to 1 over r squared, which we've seen before. That's pretty cool, right? So we have gravity increasing linearly right up until you get to the surface and then falling off as an inverse square as you move away from the gravitational body. All right, the mass body. Cool. All right. So again, not proven here, although we easily could. But now let's do example 1. I figured we'd just go ahead and use it. So in example 1, how close to the center of Earth would you have to travel in order to experience the same gravity as an astronaut that is at rest an altitude of 1 Earth radius above the surface of the Earth? Now, an astronaut that's at rest 6,000 kilometers above the surface of the Earth would be kind of problematic, right? Because they're not in orbit, they're at rest. They wouldn't be accelerating too fast at first, but they'd have a long way to fall, right? So probably not a good idea to be at rest, but you get the idea. This is just, we're running the numbers here. Okay, so part A. So we want F, INS standing for inside, to equal F above, okay? And then we have that our H in this case is just equal to the radius of Earth, okay? So then let's just write what this is going to look like. So on the inside, we already have the form of it, which I've argued for. G, M, M, and I say argue for because I justified the equations a bit, right? But I didn't show them with the calculus. Over R, this is for the radius of the Earth, and this would be cubed, and then times the variable R. That's what we're going to be solving for. And then outside, it's just going to be G, our object, whatever it is, U, right? How close to the center are U? So U are little m. And then big M for the mass of the Earth. I'm leaving off a subscript of E here because I think it's obvious. And then we'd have R plus H, right? We've done this for satellites. And here I will write it as R plus H, and then we have to square it. But I'll note immediately that H is R because we're 1 radius above. So we can just say that H is equal to R, which is nice, right? So simplify things nicely. So then I'll show some cancellations because you can tell gravitational constant cancels. So it could be in a different universe where the gravitational constant is 2 differently, if there is such a thing. This wouldn't matter, right? It's just all about distributions, right? Geometry. Big M cancels, so it would be the same on any world, okay? All right, so now we'll clean this up a tad, cancel some more things. So then we're going to have 1 over R cubed times the variable R is then going to equal 1 over 2R squared. Okay? And so then, when we solve for this, we get R is going to be 1 over the square root of 2 times the radius of the Earth. Okay? So that's where you'd have to be. All right? You have to be 1 over root 2 times the radius of the Earth. Well, it might be nice to see this as a fraction. Well, what is 1 over root 2? I'm going to put that in my calculator right now. I think it should be about 0.7. All right. All right, so yep, it ends up being 0. And there's no choice of sig figs here. So I'm just going to actually make that as approximate because up to this point it was exact. So 0.707, it's kind of fun. All right, and then just times R. So you got to be about 70.7% away from the center of the Earth. So you'd have, or in other words, you'd have dug 30% down, or 29.3% down into the Earth, and you'd be at that point where you would have a weaker gravitational attraction. You'd weigh less, you'd accelerate more slowly, and that slower acceleration would be exactly equal to someone that is 1 Earth radii above, right? With a similarly or exactly equal reduced acceleration. All right, make sense? Okay. All right, so that's our answer. Go ahead and put a box around that. Okay, and we could plug in the numbers, right? It ends up being about 4.51 million kilometers, or about 4,500 kilometers, or 4.51 million meters is the distance from the center, right? And remember or compare that to the fact that the Earth's radius is about 6,370 kilometers, or about 6.37 million meters. Okay, so 7%. Okay, and then part B, I asked you a question, which is actually a concept question, disguised as a numerical question. How far from the surface of the Earth would you have to travel in order to feel the same gravitational force as at the center of Earth? Okay? Well, at the center, r equals 0. So that tells us from our F inside equation, unless it's wrong, or unless it doesn't work for r equals 0, that tells us then the gravitational force at the center must be 0. Okay? So, 0. Okay? So the force is 0 newtons. Okay? And so then the only way for that to match F above so that would, have the form G little m big M over the radius of the Earth plus some height squared. So the only way for that expression to equal 0 newtons is for, well, r is in the variable, that's just a fixed value of the radius of the Earth. Well, that means you have to change something with h. And the only thing you can do is for h to be infinity. Okay? That's the answer. Because that's the thing, right? If Earth was the only gravitational body in the universe, hard to imagine, right? But in that case, you could go to the center of Earth and be truly weightless, right? Now, there'd be some problems with going to the center of the Earth, practically speaking, but when you're there, you'd just be floating. Because the shell theorem, right, if you believe it, unproven, tells us exactly that everything cancels out. And in fact, at the very center, it's pretty easy, right? Because you can really imagine everything symmetric. There's just as much pull in every direction. Thus, F naught has to be 0, right? If you're right there at the center, all the forces cancel out. Okay, so yeah, totally seems reasonable, and it is. Okay, there is no gravitational force from the Earth at the center of Earth. So the thing is that as you move away from Earth, the only way to have truly 0 influence is to be infinitely far away, or at least so far away that h is so much larger than r that force is negligible, right, to however many sig figs, and that's your 0 force. All right, good. All right, so we already have a student solution for example 2. The other one I wanted to show you was example 3. It's going to be our calculus example. I'm going to wrap up today's lecture. All right, so let's get through this. So in this one, we have a more accurate density of the Earth. Okay, it's not uniform. Okay, and what happens is it has a density function that looks an awful lot like this. And looking at this function, I want to quickly interpret it. One thing is it's got r. Here I have the subscript. Sorry for the inconsistency. This is r sub e, whatever you want to call it. That's the radius of the Earth, right? So that's just a constant. R's are variable, so we're used to that. But here we have some different numbers. So if we think about what this function with the minus sign is telling us, is at r equals 0, the density is 14.2 times 10 to the 3 kilograms per cubic meter. So at the very center of the Earth, the density is 14,000 kilograms per cubic meter. All right, that's incidentally about 14 times denser than water. That's our liquid iron core of the Earth. But as we move up to the surface, the density falls off. The Earth is known to have a very light lithosphere. And here we're having it fall off linearly as represented by r over r. It's not, right? I don't know, what a better function would be other than some sort of piecewise function. But the point is that as we get to the top, at least if we consider our endpoints, at the very light lithosphere, the density is dramatically different. Instead of it being 14,000 kilograms per cubic meter, 14 times the density of water, it's just the difference between 14 and 11.6, which if we think about that, let's see, so I hadn't run the numbers. Let me just do it fast. Arithmetic, right? 14.2 minus 11.6 is 2.6. So it'd be 2.6 times 10 to the 3, 2,600 kilograms per cubic meter. In other words, at the very surface where little r equals big R, the density is about 2.3 times the density of water instead of 14 times the density of water. All right, so big difference. Okay, so with that realistic Earth, what does gravitational pull look like? Well, certainly that means that as we fall down, if we went inside the Earth at first, we wouldn't be losing much gravity at all because we're just losing all the low density stuff. And then eventually, as we got closer and closer to the core, if we could, then we'd start losing it at, maybe something closer to a linear rate, okay? But it wouldn't be linear, right? So in other words, this function no longer encapsulates it because that assumed uniform density. Well, now we've refined that assumption. Okay, so in part A, what is the weight of an 80 kilogram person when they're in an impossibly deep hole that's halfway to the center of the Earth? Okay, so what we want to do here is just set up the total mass integral and then use the whole force here, okay? So the total mass integral just looks like this. So we need, and this is something that we discussed when we were talking about center of mass, in particular on the moment of inertia, because the center of mass of a sphere is always going to be the center, because we really never vary the idea of having our angular density. But we did deal with spheres that were not uniform density as a function of the radius, and then that did affect the moment of inertia. So you've seen this before. It's just been a while. So we need the total mass integral. You saw total mass integrals for rods as well. We're dealing with variable density functions. Okay, so that would be just m is integrating over dm. Okay, and that's what we're going to start with. Down here, I'll start showing the steps. Next line. Okay, so in that case, we're going to be going from 0 to r, and I, again, won't be doing the subscript with e, because that's big R means radius of the Earth. And then we have 4 pi r squared. All right, that is just the surface area, okay? The surface area of what? The surface area of a shell, okay? And then times rho, all right? Then times dr. So what are we looking at here? Well, this is the mass of a concentric shell with a infinitesimally thin thickness of dr. So this is mass of shell element, and many of you recall I've used that type of terminology before, with thickness dr. All right. So the idea is that you can then integrate these shells, these infinitesimally thin shells, one on top of another, over a continuous integral, right? Because there's not a discrete number of them, there's an infinite number of these shells, but you're integrating over them and thus encapsulating the total mass of the Earth, okay, with our given density function. All right, because again, that works because there's no variation with theta or anything, okay, or phi, right? The big three-dimensional spherical coordinates. Well, we don't have to worry about that here. All right, so we can just go ahead and solve the integral now. I guess once we plug everything in. So 0 to r, 4 pi r squared, that's just the surface area of a sphere, by the way. And then times r 14.2 minus 11.6, little r over big R, okay. And then times 10 to the 3, because we need the correct order of magnitude, and then just dr. All right, so let's go ahead and actually do the integral. All right, so when I do the integral, the only thing I have to worry about is going to be the r. Okay, so let's see. Yeah, so I guess I gotta see where it's going, because we have r squared. Oh yeah, because I have the r squared, right. So let me do this a little bit more cleanly. I was checking my own notes on this. So what this would look like if we do let's pull out the constant, and then in brackets I'm going to kind of show the integration, and then I'm going to show the limits on the edge of the bracket. So then I would have r squared, or I'll put the number in front, 14.2 r squared, and then, well, if actually, to be fair, if I've already done the integral, it would be r cubed over 3. So let me actually clean this up one last time. So 14.2 r cubed over 3, and that's just from simple rules of antiderivatives for polynomials, and then minus 11.6 times r to the 4th over 4. Because if I distribute this r squared n, it becomes r to the cubed, just like this, when I distribute the r squared into here, it was r squared. Of course, when I do the antiderivative of r cubed, it's r to the 4th. Okay, so then I have r to the fourth over 4. And then I'll evaluate from the limits from 0 to r, which means that all my variable r is just going to become big R. And I don't have to worry about the lower limit because everything zeroes out. Okay, and everything's still times 10 to the third, which I guess I'll arcally put over here. Okay, all right, and so let's do this then. So what can I factor out? Just taking a look at that because I could. I have my 10 to the third. All right. Yeah, looks good. Looks good. Okay. So anyway, so that's just going to be 4 pi times 10 to the third times r cubed. Okay, yeah, look, that's good. That's exactly what we wanted. And then times just some numbers, 14.2 over 3 minus 11.6 over 4. Okay, and I'm just going to turn that whole expression into another decimal because we started with decimals anyway, right? We didn't end up with clean fractions, so we'll just turn it into a decimal. Okay, so thus our total mass is, well, let's see what that decimal gives us. So 14.2 minus 11.6, 14.2 divided by 3 minus 11.6 divided by 4. All right, so 1.83. So then, and then we'll go ahead and just multiply that by 4 pi. So 4 pi times 10 to the third times 1.83. Okay, so then we end up with 2.30 times 10 to the fourth r cubed. Okay, and this would be this, if we're thinking about this as a mass, that's actually just, this represents our density in a sense. It has units of density, so it's going to have kilograms per cubic meter. And then we'll just multiply that by cubed, okay? And that's the total mass. Now, if we wanted the number, right, if we wanted the total mass of the Earth, all we'd simply do is just put in the radius here of 6.37 times 10 to the 6 meters, and this would literally give us the mass of the Earth, okay? So and that's the whole point. And again, these numbers are fairly accurate. That actually give you a value that's pretty close to your published value of the Earth, okay? Now, what we're going to do with it, however, is we're going to put it to use to actually find the force, okay? So we're going to then use the same approach of pointing out that F enclosed is just going to be G M M inside, okay? All right. So let's see. Actually, I think I want to change one thing because I was doing, going to such lengths here to be integrating to the total radius. But of course, that's not what I want to do. I want to have a density that is encapsulating it in terms of little r, right? That's the whole point. And so let's think about this. So if I want to actually then, because I don't want to find the total mass. I want to find the mass enclosed inside. That was the whole point here. Okay, so then I'm going to make a change here, and it'll be a change for the better. Okay, all right, because then what we'll do is then we can just go ahead and integrate to the value we want. Yeah, but we want to clean this up. Yeah. I'm prematurely finding the total mass. Okay, but it'll be a quick fix. Okay, so I want to call this inside. I'm going to integrate from 0 to r instead of 0 to big R. That means my integral won't clean up as much, but that's all for the better, okay? Because we'll have a chance to do that later. And then, so then what I'm going to have here, so let's just clean this step up. So then what this will look like is r cubed. Let's see, because essentially it's just, I'm just getting the correct form, okay? So, and yeah, exactly, I'm just getting the correct form. So 14.2 over 3, and then minus 11 point, I'll write like this, 11.6 over 4, and then r over r. Right, so we kind of got back to something that looks a lot like we had before, except now it's specifically appropriate to the shape of a sphere, right? Because before we were just given a mass distribution, right? That could have been a mass distribution for any shape. What we've done now is via the integral and the idea of integrating over these concentric spherical shells is we now have a mass inside that actually represents a distribution that is spherical in shape. Okay, and you'll see what that looks like here. Okay, so then as a value, it's going to be just 4 pi times 10 to the third. Okay, which I'll just leave as 4 pi. Don't have to turn that one into a decimal. Okay, and then r cubed. Right, and actually I can put units on this. This actually is kilograms per cubic meter. All right, and then times r cubed, the variable r cubed. And then 14.2 divided by 3, okay, which is 4.73. And then minus 11.6 divided by 4, which is 2.9. And then r over r. Good. Okay. So now that's my mass inside. So I'll be plugging that in. And then I'm going to have, that's going to be over r squared. Okay, getting this from, universal law of gravitation. And again, if this had been a uniform mass distribution, do you remember what mass inside looks like? Right? Obviously this function is much cleaner, right? It's just m times r cubed over big R cubed. Okay? Now, do we still have that sort of form? Yeah, right? We still have the same units, but it just has a different look to it because it's a different distribution. Okay? It's customized. Okay? So then we can go ahead and plug in R cubed. So I have big G, little m, okay? And then 4 pi times 10 to the third kilograms per cubic meter times R cubed 4.73 minus 2.9 r over r all over r squared. Okay? Now, we're going to have something that looks, again, somewhat linear, but it's not linear anymore, right? Because before it was just exactly going to be proportional to r. Okay, well now, yeah, it's proportional to r, but actually if we distribute the rn, we can see that there's one term that's proportional to r, and there's another term that's proportional to r squared. Okay, so it's a different function fundamentally. Okay, our enclosed force is a different function. All right, well, but that's great. We've got our function now. All right, we have the force inside, the gravitational force inside our non-uniform density sphere, not uniform in the radial direction. And now we can set that force equal to whatever we're asked to in order to then solve for r. In this case, we want to find the force at 1/2. Okay, so it is the weight. Okay. So then force inside when little r equals 1/2 big R will be what? Well, let's plug in the numbers. Looking good. All right. In this case, m is 80 kilograms. Okay, so we have 6 point, all right, and then 6.27. Just been using Planck's constant a lot recently. I keep getting them switched up, so I'm just gonna actually check it real fast. And it's late, and I don't remember the number. All right, let's see. I think I have it here. Yep, 6.67. So 6.67, notes times 10 to the negative 11, Newton meter squared per kilogram squared times 80 kilograms, okay, and then times 4 pi times 10 to the third kilograms per cubic meter, okay, and then times r, which is 1/2 big R, okay. Now we need the mass of the Earth here. So actually we need a little bit more space, long line. Okay, so we'll put that in there. Okay, so then times 1/2 r. Yeah, and I'll just put this in. So that's going to be 1/2 times the radius of Earth, so 6.37 times 10 to the 6 meters. Okay, and then everything that's an attribute of the specific distribution, the 4.73 and the 2.9. And then we have here, if we're looking at this term, that would be 1/2 r over r, which would just be times 1/2. Right, looks great. Okay, are we getting the right units? Are we going to be getting newtons? Well, if you look, we're canceling out the kilograms. Okay, so we have a kilogram. If you take a quick look, right, the kilogram and the kilogram cancel the kilogram squared. Our meter squared is going to combine with a meter to cancel with the meter cubed in the denominator, and then we're just left with newtons. Okay, all right, I'll go ahead and leave those so we can clearly see what units canceled out. Okay, that's a good sign too. It's always a good idea when you're doing these integrals and the antiderivatives of polynomials just to check your work there. All right, times 10 to the negative 11, I'm just plugging the numbers. Okay, times 80 kilograms times 4 pi times 10 to the 3, and that's just to get the densities realistic. All right, and then times 0.5 times 6.37 times 10 to the 6 meters, okay? And then times 4, let me get the exact number, 4.73 repeating actually, minus 2.9 times 0.5. All right, so we have 701 newtons. That's beautiful. That is so beautiful, right? Because it's just such a fascinating number, right? Because it's such a wonderfully realistic number. Because how much would this 80 kilogram person weigh on the surface, right? Well, we can say compared to weight on the surface, where they would have a, we'll just say, the weight is equal to the normal force, so I'll just call it the normal force, and that's just mg, and well, that would just be 80 times 9.8, of course, and that is 784. So they're not that much lighter, my goodness, right? They drilled halfway down to the center of the Earth with this singular misguided goal of making themselves lighter, because they know, you dig down, Shell theorem says the mass above cancels out, and yet they're just 80 newtons lighter, right? They're just like less than a seventh lighter, right? They're still over 8/7 their original weight, In fact, if we take 701 and we divide it by 784, we could say exactly what their percentage is. They're still 89.4% their weight on the surface, even though they're halfway down. Now we know that being halfway down, even in uniform density, wouldn't reduce your weight dramatically, or maybe not, it wouldn't reduce it by half, certainly. But here, because we have this density function, which gives, rightly so, all the denser matter placed closer to the core, well, there you go. You're still got all of that pulling you down, and not so much canceling out above. All the lighter matter canceling out above. All right, so in fact, let's find the percent error between using the uniform density and the more accurate denser core distribution. So what is the percent error between this more accurate weight and that estimated with uniform density? All right, well, so we can quickly find the uniform density. See if I have space here. Maybe I'll bleed over the next page. So for uniform density, F inside for R equals 1/2 R would just be, let's see here, that's the one I wanted to look at. Oh, it's referring to something over here. Right, just give me one moment. There we are. Okay, so I just want to not have to flip back and forth. So we'd have F inside would then just be big G M M divided by R cubed times 1/2 R, okay? And so then that would be G M M over 2R squared, okay? Well, that's exactly half the gravitational pull that we feel on the surface. So yeah, actually this one, I guess that's the thing with the uniform density, it's linear. Yeah. So I think I was mixing because a second ago I said, oh, well, even with the uniform density, it wouldn't, but actually with the uniform density, the force is linear. That's the whole point. And so it would be exactly half the force. So if it's half the force, then we would simply take 784 and divide it by 2. Thus, it's just going to be Fn over 2. Because this whole business right here, Gm times big M over R squared, that's exactly Fn. Okay? It has to be because we know that this is equal to Ma, okay? And A is equal to G. So it's just equal to mg. Well, we know that mg is by definition Fn, right? And the only difference is we just have a 2 in the denominator. All right, beautiful. Okay, so it would just be 784 divided by 2. So let's see, divided by 2. Well, that's 392. Well, that's nothing to scoff at, right? These are egregiously disagreeing values, right? Comparing 701 by having the much denser core and the light upper layers of the Earth compared to the uniform density. Wow, my goodness, right? So then the percent error, I'm just going to just make enough space here, if you'll indulge me, because I think we can definitely fit this in here. Okay, so we can just do on the last line. Okay, so then the percent error is then just going to be the 701, just because I want the absolute value, minus the 392, okay? The units are canceling out, so I won't write it in. And then we're going to divide by what? We'll divide by the more accurate number. So we'll divide by 701, multiply it by 100, see what we get. All right. Wow. Yep, better use the right distribution. 44.1% error. That wouldn't be great for a lab, right, in school. That certainly wouldn't be great for making estimates of the gravitational pull, And of course, this has bigger effects other than just imagining, a person digging a hole in, some sort of Jules Verne-esque, imaginary, well of some sort. No, I mean, this matters, right? Because this tells us kind of how things behave, right? Because the Earth, right? These layers, the mantle of the Earth, right, where the convection is happening, it's still being pulled on with a lot of force, way more force than a uniform density model would suggest. Well, that means a lot, right? That means that all that mantle is heavier than a uniform density would suggest. So then that dense core means that all that liquid mantle is actually being pulled on, right? Or actually, it's actually more like a solid mantle, because it's the idea is that the core is truly liquid, and although the mantle is convecting, it's more like rubbing together like a solid. But not getting into geophysics or geology here, or it's just there's a lot of real life consequences, and it's so fascinating because it's such a big difference. Okay. So anyway, hopefully it was a good kind of review of doing the calculus that would be relevant here. And this is the exact same approach if we wanted to do a total mass integral. This is the exact same approach that we would want to take to show the formulas that I gave you in the key formulas for these lecture notes. All right, well, that's it for the final lecture, Lecture 30, and it's one accompanying video. Thank you so much for watching, and happy studying for the final.